Today, we will be discussing our laboratory findings. Today, we're discussing strain hardening or work hardening, the process where metals gain strength and hardness through plastic deformation. This phenomenon occurs below a metal's recrystallization temperature, typically at room temperature. At a microscopic level, deformation triggers the generation and movement of dislocations within the crystal lattice. As these dislocations multiply, they become entangled, making further movement difficult. Consequently, it requires more stress to deform the material, which increases its yield strength and hardness while reducing ductility. In this study, we evaluated the hardness of copper and aluminum before and after open die compression forging. By focusing on these two metals and a single cold working technique, we isolated the mechanical changes.
For our methodology, importance of maintaining constant aspect ratio, all specimen maintained at constant height to diameter ratio because it ensures uniform stress distribution during compression. Effect of varying aspect ratio, it causes non-uniform stress distribution, taller specimen, shorter specimen, and reduces reliability of hardness-strain relationship. In sample preparation, we prepared the specimen using copper and aluminum materials. Each sample was fabricated with a uniform aspect ratio of 1:1. In open die compression forging, the specimen were placed between two flat dies in a hydraulic press. It has compressive force was applied gradually using a hydraulic pump until the desired pressure was reached. After forging, the top surface of each specimen was prepared for hardness testing. Proper surface preparation is critical to obtain accurate results. Hardness measurement and sources of error. However, there are several possible sources of error. Measurement inaccuracies in initial and final dimension may affect strain calculation and interpretation of strain hardening behavior.
Now I will discuss the result and discussion obtained for the laboratory of strain hardening. So in here, we have here the table 1 for experimental design. Using open die forging and two-way ANOVA, the study investigate if increasing pressure 20, 30, 40 megapascals significantly raises the hardness of aluminum and copper via strain hardening. The statistical model ensures high reliability by isolating the effects of pressure from potential measurement, inconsistencies of or trial variability.
This table summarizes our findings by comparing our experimental data to theoretical values found in engineering literature. For copper, we were very close to the expected range, landing at 0.56. For aluminum, our result of 0.53 was higher than the typical 0.25 to 0.35 range. This discrepancy is actually a great discussion point. It likely stems from the specific alloy compositions of our samples or the initial grain structure of the material before we began testing.
Now I will discuss the statistical analysis of this laboratory. Now is the table 3 for the two-way ANOVA for aluminum. The two-way ANOVA shows that applied pressure significantly increases aluminum hardness, which shows that p-value is less than 0.05, confirming strong strain hardening due to compressive deformation. Trial results were consistent and not statistically significant, supporting the reliability of the findings. Here is the two-way ANOVA for copper. It indicates that pressure did not significantly affect copper hardness at the 95% confidence level, which shows that p-value is greater than 0.05, even if a slight increasing trend was observed. The trials were consistent, but overall evidence for strain hardening in copper remains less conclusive than in aluminum. So in here, the result shows that the pressure does not significantly affect copper hardness since its p-value is 0.0655. It is above the 0.05 significance level, supporting the null hypothesis. In contrast, aluminum shows a significant relationship between pressure and hardness with a p-value of 0.022, confirming that increased pressure meaningfully improves its hardness. The figure 1, engineering stress versus degree of cold working for copper. So as cold work in copper increases from 1% to over 42%, engineering stress rises from 0.16 megapascal to more than 0.31 megapascal. This shows that copper becomes stronger and can handle greater loads with higher cold work. The increase in strength is caused by strain hardening, which where more dislocations in the crystal structure resist further deformation. Now is the figure 2 for the engineering stress versus degree of cold working for aluminum. So as the degree of cold work in aluminum increases from about 8.74% to nearly 90%, engineering stress rises from around 0.17 megapascal to over 0.35 megapascal. This demonstrates that aluminum becomes stronger as it undergoes greater plastic deformation. The strength increases due to strain hardening, where higher dislocation density in a crystal structure restricts deformation. Hardness values versus degree of cold work for copper. So as the degree of cold work in the copper increases from 1.11% to 42.66%, hardness rises from 0.848 hardness value to 0.983 hardness value, showing a nearly linear increase in hardness. This trend confirms that greater plastic deformation strengthens copper through strain hardening, improving its resistance to indentation.
Figure 4, if you look at our results here, you'll see a clear trend by increasing the cold work from 10% to 90%. We've significantly boosted the aluminum hardness. This happens because we are essentially cluttering the atomic structure of these locations, making it much harder for the atoms to slide past one another. It's a great way to strengthen a part, though we have to be careful not to make the material too brittle for its intended use. Lot of copper, true strain versus true stress. We are looking at the material's flow curve. Notice how the line slopes upward. This is strain hardening in action. As we stretch the copper, increasing the strain, the internal structure becomes more tangled and with dislocations, meaning we have to work harder and apply more stress to keep it deforming. Our linear model shows an R2 of 0.97, proving that for this range, the relationship is very predictable and consistent. In this slide, we're looking at the true stress-strain relationship for aluminum. You'll notice the trendline equation y equals 1.1049x plus 0.1051. That slope tells us exactly how much the material happens as we deform it. With an R2 of nearly 0.95, our data shows a very consistent strain hardening effect. Essentially, as we stretch the aluminum, we are making it harder to stretch further because of dislocation pile-ups within the material's grain structure.
Straight hardening show a direct relationship between plastic deformation and mechanical properties. Aluminum and copper both exhibit increased engineering stress, also increased hardness with cold work. Strong positive correlation between true stress and true strain with high R-squared value. Support dislocation theory. Higher dislocation density is equal to higher strength. Straight hardening behavior is material dependent. Aluminum show higher sensitivity than copper. Aluminum strain hardening coefficient higher than expected. Possible causes is prior cold work, alloying variation, and experimental errors. Here are the possible errors. Barreling effect due to friction and uniform deformation. Lead to overestimating of stress value. Other sources of error. Uncontrolled material condition, measurement limitation. And for the improvement, use annealed verified specimen, applied lubrication, and increase trial for more data. And that's all. Thank you.